Whenever you click Buy Now on something, have you ever stopped to think about what happens in those first few hours? We're about to go behind the scenes into this silent, super efficient world of the modern warehouse. It's like an invisible orchestra that just springs to life the second you place your order.
And just think about the scale for a second. We're not talking about a few hundred packages. We're talking millions, millions of totally unique items, from a tiny gadget to a giant TV, all have to be found, packed, and shipped out almost perfectly every single day. I mean, how do they even pull that off? Well, it's tempting to just picture this army of robots running around, right? But the real secret sauce, the magic, it isn't really about any one machine. It's about the system, this invisible intelligence that conducts everything. It's a symphony of movement, really, a carefully choreographed dance of autonomous flow. So let's start by meeting the actual performers in this orchestra. The robots themselves come in a few key flavors, and each one is basically a specialist, designed for a very specific role in this huge logistical puzzle. Okay, so at the highest level, you can really split these systems into two big buckets. On one side, you've got continuous systems, like good old conveyor belts. You can think of them like a highway, right? They provide this steady, constant flow that's just perfect for when you're moving a ton of the same thing over and over. But on the other side, you have intermittent systems. These are the robots that work on a task-by-task basis, and they give warehouses all the flexibility they need to handle a constantly changing mix of products. Now, this is where it gets really interesting, because you see just how specialized these things are. First, you have AGVs, or automated guided vehicles. These guys are the workhorses. They follow fixed paths, literally like trains on a track, which is perfect for high-volume, repetitive jobs. Then you have AMRs, the autonomous mobile robots. These are the explorers. They've got sensors all over them so they can navigate on the fly and work around people or obstacles. And then you've got these incredible rack-climbing robots that literally scale the shelves to use every last inch of vertical space. It's amazing. Okay, so we've got our robotic workforce, but, a bunch of robots with no rules, that's just chaos. So the next layer of this whole system is the set of invisible instructions, the rules of the road that direct all the traffic and tell everybody exactly where to go. This slide just nails the two main philosophies for how these robots move. Fixed path systems, like we saw with the AGVs, they're like train tracks. Super efficient, super predictable, but totally inflexible. You can't just decide to take a scenic route. Then you have the variable path systems, the ones the AMRs use. These are much more like city streets. They give you incredible flexibility to find the best route in real time, but you need a way, way smarter navigation system to avoid turning the warehouse into one giant traffic jam. And who's making all those routing decisions? That's the next big question. In a centralized model, you have one master computer that's like an air traffic controller. It sees the whole picture, and it gives very specific instructions to every single robot. It's fantastic for optimization, but if that one central brain goes down, the whole system can grind to a halt. The other option is decentralized control, and the best analogy for this is a flock of birds. Each bird, or robot, is making its own decisions based on what's right around it, communicating with its neighbors. It's much more resilient, but it can be a lot harder to guarantee that it's perfectly efficient. So, how do you get the best of both worlds? Well, a lot of real-world systems use this really clever compromise called zone-based control. Basically, you just slice up the warehouse into different zones. Robots mostly stay on their own turf, which makes the traffic problem way simpler, and then when a package needs to move across the building, it's just handed off from one zone's robot to the next, right at the border. It's a really practical, elegant solution. Now that we get the players and the rules, let's talk about what happens when things go wrong. Because in a system this complex, the name of the game is finding and eliminating bottlenecks to keep everything flowing as smoothly as possible. Seriously, with all this incredible technology, all this advanced planning, millions and millions of dollars of hardware, what do you think is the single biggest problem they fight against every single day? Congestion. Yep. It's just like rush hour traffic in a big city. A robot traffic jam is the absolute worst-case scenario. It can ripple through the entire system and bring a multi-million-dollar operation to a dead stop. So to fight congestion, engineers measure absolutely everything. Throughput tells them the big picture, how many items are moving per hour. Cycle time zooms in on how fast a single order gets processed. They even track energy consumption for every move. But the one metric that keeps them up at night is blocking probability. That's the one that directly measures how often robots are getting stuck, and it's their number one enemy. And this leads to a really kind of counterintuitive point. You'd think, hey, if you want things to go faster, just add more robots, right? Nope. Turns out, after a certain point, adding more robots just adds to the congestion. The whole system actually gets slower, not faster. The key isn't having more robots. It's about smarter scheduling for the robots you already have. And that scheduling is getting incredibly sophisticated. Take something called energy-aware scheduling. Here, the system doesn't just find the shortest path from A to B. It actually considers the weight of the package a robot is carrying. So it might send a robot with a really heavy load on a slightly longer but flatter route to save energy. And when you're talking about thousands of robots, that has a huge impact on operating costs and sustainability. So, where does all this head from here? Well, this constant chase for perfect, frictionless flow is always evolving, and it's leading to some really fascinating new challenges and innovations. You see, the future isn't just about faster robots, it's about smarter brains. The physical robots on the floor are just the muscle. The real intelligence is in layers and layers of software called the automation stack. This includes things like the Warehouse Management System, or WMS. That's the master brain that knows where every single item is in the entire building. Getting all these software layers to talk to each other seamlessly, that's the next great frontier. And the challenges that are left to solve are huge. How do you schedule a fleet of 10,000 robots instead of just 1,000? How do you prove that a decentralized flock of birds system is actually safe to have around human workers? How do you get robots from 5 different companies to all speak the same language so they can work together? These are the big questions that engineers are trying to answer right now.
So yeah, the next time you click that button, you can picture this whole invisible orchestra springing into action. This amazing system of robots and rules and software all working together. But as these systems get smarter and faster, and they solve that problem of congestion inside the warehouse, it makes you wonder what new bottleneck is going to appear just outside its doors. That's something to think about.